The final challenge in the Pwn category was Infinite Descent. This challenge only had 3 solves, so not a well-solved challenge or a highly solved challenge, but at some point during the CTF, the challenge author mentioned that this challenge was actually free points. During the CTF, I did not solve it. I think I tried at the start of the CTF, and I saw it was a QEMU binary, it was ARM. It didn't have a Docker file at the time. I think the Docker file was added later. Like I tried to get it running and I don't know, I gave up pretty quickly. But now that I've actually gone through and I've read other people's write-ups, it really was a pretty simple challenge. I kind of wish I had spent more time on it. It's pretty cool. Like I said, I did not solve the challenge, as you can see. There were 2 write-ups I referenced. I highly recommend checking them out. Seraphin is the challenge author, and so they wrote an explanation. Again, recommend checking this out. Also, the first person who got first blood also did a write-up. I think they played by themselves and they came in like 5th place, so super impressive. But yeah, highly recommend checking this one out too. blog maple3142.net. So like I said, I highly referenced off their work, and really I just wanted to see what the challenge was about and solve it myself after looking at the solutions. So anyways, if you download the files, like I said, it is a ARM binary, and so we're going to have to run it in QEMU. This is what it looks like. We can see there's a flag at the top. There's a couple of buffers. So I had to look this up. So apparently there's something called semicall. And so this is a way. So the idea is this program is supposed to be run on a embedded piece of hardware. Specifically, they actually tell us the device. It's running on this. It's a LM3S, whatever this is. Apparently it's some chip. And so we have the C code, it gets compiled down to ARM, and we don't actually have this piece of hardware, so we're going to emulate it. And so we emulate it on this QEMU system ARM thing. And so this is the machine, it has this CPU, I guess this is memory, I'm not really sure. Some character devices, so it's going to use standard in. So this semi-hosting stuff is interesting. So this is apparently how the host machine and the actual target can talk to each other. And I think this is implemented through like some custom instruction. It's a little bit confusing what's going on here, but I guess somehow this allows the target and the host machine to talk somehow. But it wasn't too necessary for the challenge, but this is how we get the actual output. What else? Like I said, the target, device, not really sure, machine, Excel, I think TCG stands for Tiny Code Generator. I didn't quite understand what this was, but it didn't seem too relevant for actually like running and exploiting the challenge. And then some other stuff, and display none. And then these are the debug flags. So anyways, like I said, the hardest part of this was actually getting set up. So thankfully, oops, how that happened. Some way during the CTF, this Docker file was released. This one's actually modified quite a bit. I tried to get Pwn debug to work. I couldn't get it working. But anyways, the Docker file is just Ubuntu 2204. It installs QEMU system ARM. And then afterwards, these are my additions. So I also installed GDB multi-arch, tmux, and git. And then also some utilities, because I also tried to get gep to work too, but I couldn't get that. It just wasn't working for some reason. And then also tmux. Oh, tmux is installed twice, so we don't actually need this. Cool. So let's go back to the program. So like I said, we have some way for the host and the target to talk, but it's not actually too important. The only real important things are this function and the main function. Cool. So let's start with main. So it says, welcome to my tunnel. We're going to descend. And then it says you have run out of energy, and your final message is this. Cool, okay, nothing too exciting. Then we have this descend function. How many characters do you want to write to the ground? Up to 4 kilobytes. Send the digits and then the new line. So it'll read a number, do string to long, and then write end characters. So we get to write characters. It's going to put it on the stack. But what's interesting is then it calls descend again. I think another hint was given during the competition. Oh yeah, so how is memory laid out on the binary that's very different than a non-embedded binary? Also, if you're scared of QEMU, it might help you to know that you can debug the binary with -s. I think this one says the process starts, but it waits until a debugger connects. And I think this one is it'll open up a remote debugging port 1, 2, 3, 4. Cool. So we know that there's something about how things are laid out in memory, which is different than a normal process, is how we're going to be able to exploit this. We can kind of see an issue here. So descend is calling descend, so we're doing a recursive call. I think it's common in programming when you have this recursive thing, if you like call into the same function too many times, you'll eat up the entire stack and the program will crash. So that's common. But otherwise, I'm not seeing too much. But we do, from this, we can kind of guess what we're supposed to be doing. So it's going to descend quite a ways, and when it's done descending, it's going to print out a last message. I feel like normally in CTFs, either we're going to do, it's in the pwn category, so maybe we're going to be doing some real corruption, or somehow we need last message to print out something interesting. It's doing a write, so it's probably not a printf. So, and the fact that there's like this extra thing here kind of makes you think that you're going to have to put the flag in here. And we can also see it's being used, so last message is equal to input, so something's going on. And like we said, we have the flag up here. And it's also interesting that this is volatile, so I think it means this will be in a different section within the binary, within the memory, but I'm not always too sure how that stuff works. Anyways, like I said, the hardest part was actually just getting this running. So thankfully a Docker file was provided. You can install some stuff. I think there was a run script. I got rid of it, put it into a makefile, and so we can run debug, and actually debug it. This is what the solve script looks like. This is how I use to actually run it. So make process, and then I just do a make run shell. So let's just jump in and start seeing what it actually looks like. So I'm going to split to 2 different panes. I'm going to run it. So to run it, I'm just going to do Python 3 solve. I think I put a sleep in here. Yeah, so there's a sleep. And then we can do make debug, and this will attach a debugger. All right, so a couple of things. Like I said, we're not really sure how things are laid out, and for some reason GDB seems to just be a little bit broken when it comes to this. Like I said, I want to use either gef or pwn debug, and so I can like look at VM map, but none of that stuff works. I think you can also do info proc or something like that, but I think since it's like a weird remote QEMU ARM binary, you're kind of limited. You can do info file. I'm not sure how reliable this stuff is. Like, it doesn't show where the stack is, but after playing with it for a while, it does look mostly correct. So we'll eventually see that text is actually these addresses, and I think the stack is a little bit higher than this, but actually no, I think that is data. So these are correct, it just doesn't show the stack. But we can look at info reg and actually get the stack address out. So we can see the current stack pointer is here. And it's kind of fun, you can tell this is a ARM binary. We don't have like RAX and RBX, we have R0 to 12, which is pretty cool. But anyways, so we have a stack pointer. Again, I was trying to find the variable, so somehow we want to find this. What's weird is if you print this out, it says cannot access memory at this address. So this was kind of confusing. So instead I started just playing around. So we have a couple of things that are interesting. This is a stack address, We don't know what this is. Don't know what that is. Oh, sorry, stack address. Not really sure what that is. We can see semcall. This is our program counter. So what I did, I wasn't sure if maybe data variables would be defined at the bottom. So I just started examining strings. Here, we can see this is some vectors. So maybe this is like interrupt service vectors or whatever those are. Nothing too exciting. So we're just going through strings. Where are we now? We're at 200. Let's do 40 strings, OX 200. We're still in vectors. It's a lot of vectors. Oh, we're going up. Let's go back actually. 400, 300, 4,000. Okay, so now we're semi-call. So these are our functions. So we're in the text segment. We can see the write, read, and descend functions. And we don't really see any variables defined here. We're looking for these strings. Fake flag and you didn't do anything. So we can keep jumping. There's some reset handlers, start. Looks like some libraries got included, restore non-core regs, some unwinding. Doesn't look relevant to what we're doing. I don't know why it stopped there. E3D. Keep going. Oh, maybe we just can't do 20 strings. Unwind, GDB execute, abort. This all looks like library stuff that we're not actually going to be using. System, that's interesting. So maybe we would be exploiting something. String lang, some more functions, and then here we go. We finally found some data. So it looks like our data is being written to, or is saved in this memory address. So we have fake flag. There's a space in front here. So I think our flag is actually at 2740. So we want to save that, and I have it saved in the save script. The other thing we were interested in is this last message thing. We can see last message, the contents of last message, you didn't write anything. Should be somewhere here. Yep, so it's right after the flag. And yeah. So one thing that's interesting though, so last message is a pointer to this. So there's actually an address. So the last message is actually in memory at this location, but it points here, or here. So I'm not really sure what this section is in the binary. I think it said this was the data section when we looked at info file. 2070, so it is the data section. So I guess the variable pointer is created here, and then it points into the data that's at 2846, so it points into data that's in the text segment. Cool. Anyway, so we kind of know we have two addresses. Next, if we look at the registers again, we can see stack pointer is currently at, this is a 32-bit address, and it's 2000FF90. Cool. So based off of the hint and just kind of thinking about things, we want to overwrite an address that is located at 200070, and the current stack pointer is here. The stack is also growing down, and just know that from playing with the binary, and we're able to call in descend, call this descend function over and over, and every time we call descend, it's going to add stuff onto the stack, and it's going to add a pretty big chunk onto the stack. 4096 bytes at least of data goes on the stack. So we'd only need to call this function a couple of times, and as long as we don't get some like memory mapping error, we should be able to just go from this high stack pointer, go all the way down, and clobber the data section. And it turns out that is what we're actually supposed to be doing. Again, thanks to the amazing write-ups that I showed earlier from, I think, Seraphin and Maple. And so that is, like I said, that is the solution. So what we're going to do is we have the flag address, we have the buffer we want to overwrite, we have our current stack pointer, so we can calculate roughly how many rounds it's going to be, and it'll print out, it's roughly 15. Yeah, I have it right here, 15.9. And so what we can do then is for 15 rounds, we will send it 4 kilobytes of data, and instead of just sending A's, we can send the flag address over and over and over. I thought we could do it 16 times, but when I did it 16 times, it seemed to be clobbering something. So instead you have to be a little bit careful. I tried to do like 3,100, but that still didn't work. So eventually you whittle it down, and this is also what the challenge author had in their solve script was 3072. But then you send the address over that, it'll clobber it a bunch, and eventually it'll clobber this variable, last message, with the address of end of tunnel. And then, so when the program exits, it'll just print out last message and you win. Cool. So one thing that's a little bit silly is these processors are pretty slow. I mean, I guess they're like low powered, and that's supposed to be impressive, but you can see I'm on round 3, round 4, and so this is the processor processing 4 kilobytes of data. Round 5, and we want to get to 15 rounds. So definitely takes a second. Trying to think if there's anything else that was interesting while this is running. I didn't look into this too much. I guess this is GCC ARM LD. I think this is useful if you were to build the file. A make file was also given for building it. I think I deleted it though, because I didn't plan on building anything. And yeah, I think some notes were also given in the README if you want to build it. But it didn't end up doing that. Anyways, it looks like it made it to the end. Again, it's still processing stuff. And cool. So the descend function exited. We sent 0 bytes. And then it says, okay, you've run out of energy, and your final message is, there's the flag. So again, the challenge really wasn't that difficult. Like if this was on a normal x86, 64 sort of ELF binary, like this would have been a baby challenge. But I think just because it was ARM and you had to run it on QEMU and get everything set up, this was the least solved challenge. Even though it was just like a very simple kind of, not quite a stack overflow, I guess a stack clobbering attack, but very cool. Very excited it's my first time pwning an ARM binary like this, so thanks for the challenge.